So now we are going to start to analyze nonlinear system of difference equation. Just to close what we have seen until now about nonlinear equations. So if we have a nonlinear equation given by this, we find the steady state is given by this when this happens, and then this, so here is this steady state, and this steady state can be unstable or stable, and it will be stable if the derivative at the steady state is smaller than 1. Okay, we are going to move to nonlinear systems, but we are going to see that it's similar what happens. So consider the system of nonlinear equations. So now here we have x and y, which depend on each other, and f and g are nonlinear functions. And the steady state, it's when the system doesn't change anymore, will be given by something like this. And so we do a similar approach here. So we suppose that we are interested on what happens to the point. Okay, where I erase it. So file. Okay, I was trying to put a new page, but I think I don't know how to do it right now. So the point is that we suppose that we are interested to know what happens around what's going to happen to xn and yn around the steady state. So we suppose that there is some perturbation here. Why? Okay. Okay, yeah. So we start with this, and then we do the same approach as we did before. We find the first order Taylor approximation for, but now it's a vector for f of x bar plus delta xn plus, and so we find the first order approximation for this, and then we are going to arrive into a system for the perturbation, and J is the Jacobian matrix, which is given by this, evaluated at the steady state. Okay. If you want some detailed calculation of this, just let me know. I can provide. Now we got into a system which is so like this, right? for the perturbation. And we have seen on the beginning of this lecture how to deal with linear systems. So we suppose that the solution of this system will be something equal some constant 1 times the first eigenvalue to n times the first eigenvector plus a constant 2 times the eigenvalue to n times the eigenvector. So we can do some similar analysis than that we did for the nonlinear equation. So we can see again that this perturbation will tend to 0 if this lambda 1 and 2 are between 0 and 1. Okay, so this is the conclusion. Let's come back a little bit. So what I say is that we can use the linear theory for different systems to study the stability, and we are going to remember how to do it. So for a given steady state x bar, so this big X bar, it's a vector now. So we need to find the eigenvalues through the roots of the characteristic polynomial. And J here is the Jacobian matrix, okay? And this result will be a quadratic equation in which beta, so we have here lambda square minus beta lambda plus gamma equals 0. So that's our characteristic polynomial, in which beta is the trace of the Jacobian matrix and gamma is the determinant of the Jacobian matrix. And for stability, we have to determine whether the eigenvalues are of magnitude smaller than 1. So we want that lambda 1 smaller than 1 and lambda 2 is smaller than 1. And now I put here some exercises as homework. I can solve some of them with you.